Two-class classification. In the previous lecture, we learned about linear classification. We learned conceptually and also about the different methods through which we can do linear classification. Here, we are going to do a deep dive into two-class classification. That is, we want to classify where there are only two classes, C1 and C2. So whenever you get a data X, you want to decide whether this is of class C1 or if it is of class C2. So this is the task. What do you have to have first is a discriminant function. That is, as we discussed in the previous lecture, there are three methods of doing classification. One is using a discriminant function, which will directly tell you that it belongs to class C1 or C2. Second one is to have a posterior probability, that is P of Ck given X. And from this posterior probability, you can understand which is the class to which X belongs to. And the third method, which is a generative method, is in which you find the class conditional densities X given Ck, P of X given Ck, and from this you can find out the posterior and then you can find the corresponding class. We also discussed about the positives and negatives of that. Here we are looking at the discriminant method. We'll have a discriminant function which will work like a black box. That is, once you give the data to the discriminant function, it will directly tell you that it belongs to class C1 or C2. Let us say our discriminant function is this. Y of X is equal to W transpose X plus W0. This is our discriminant function. What is W here? It is the weight vector. X is your data, and what is W0? It is the bias. Do not confuse this bias with the concept of bias variance trade-off. The bias has a totally different meaning. Here this bias is something like, let's say you have a line like this. Here if you plot the equation of the line, it will be y is equal to mx plus c. So what is the c? It is the y-intercept. This W0 is a concept very similar to this. So that's what you call as bias. We'll get to know more about this W0 as we go along. So the first thing now is, how do you classify a point? Let us say you got a new point which is X. How do you find whether X belongs to C1 or if X belongs to C2? It is very simple. That is, if the value of y of X that you got is greater than or equal to 0, then you would say it is in class C1. What if it is less than 0? If y of X is less than 0, then you would say it is in class C2. So from this, it is very clear that the decision boundary is the line y of X is equal to 0. This is the decision boundary because above this it is class C1 and below this is class C2. So y of X equal to 0 is the decision boundary. If we plot it, let us say this is the graph and maybe this is the line. If this is the line, y of X greater than or equal to 0, maybe that is the portion above this line. So all the points that are plotted above this line, they all will belong to class C1. Similarly, everything that is plotted below this line, any point that is below this line is class C2. This line is called the decision boundary. Okay. So, okay, this is a line. So this line is the decision boundary. Here I'm considering it as a line because I'm considering a two-dimensional input space. Similar to what we learned in the previous lectures, if it is a d-dimensional input space, then your decision boundary will be a d minus 1 dimensional hyperplane. So in two-dimensional space, it is a line. Next thing is, whenever you are learning any sort of machine learning concept or anything where you are learning something and you want to be an expert on that, you should be very clear about every single concept that is associated with it. That is, anyone can simply say that this is my discriminant function. I want to train this discriminant function. And then whenever I give a value of X, if y of X is greater than 0, I would say it is C1. And if it is less than 0, it is C2. This is very simple. But you need to understand very clearly what is the significance of each term in it. Why do you use W here? Is it just a coefficient? What is the significance of this coefficient? What happens if this value changes? Similarly, what is the significance of W0? What happens if the value of W0 changes? Let us understand this in a bit detail so that whenever you see two-class classification, a linear classification, you would be very clear of all the concepts and you would feel that confidence inside. This is what we aim with these lectures. In these lectures, if you are attending, you should be very clear about every single term that is used anywhere in any equation. So let us understand it very clearly. First, let us take this term W and let us understand what is W, what difference does it make if its value changes, what is the significance of this W in this equation. Okay, let us say there are 2 points xa and xb on this line. That is xa is here, this is xa, and let us say this point is xb. Okay, so xa and xb are 2 points on the decision surface. So what is xa minus xb? Xa minus xb, it will be a vector, right? It will be something like this. It will be a vector which is along the line, right? This is my xa minus xb. So if I have 2 points xa and xb, in that case, what will be my y of xa? Y of xa. Because xa is lying on the decision surface, y of xa will be equal to 0, right? Similarly, because xb is also lying on the decision surface, y of xb, that will also be equal to 0. Agree with this? So both y of xa and y of xb are 0. What is y of xa? Y of xa is w transpose xa plus w0. And what is y of xb? Y of xb is w transpose xb plus w0. What is y of xa minus y of xb? If you do that, you will get w transpose xa plus w0 minus w transpose xb plus w0 is equal to 0. So on the RHS, 0 minus 0 will be 0, and on the LHS, y of xa minus y of xb, right? Here w0 and w0, these two will cancel out each other. So what remains is w transpose xa minus w transpose xb equal to 0. If you take w transpose out as common, then you will get it w transpose into xa minus xb is equal to 0. This is the equation that you got. This has a lot of meanings. This equation w transpose into xa minus xb, this has a lot of meanings, and this is going to explain the value of w here. What is w, right? First of all, when I write w transpose into xa minus xb, that means it is a dot product between w, the vector w, and the vector xa minus xb, right? So if it is a dot product, that is w dot xa minus xb is equal to 0. This is what it means. Whenever you have a dot product equal to 0, what does that mean? When will the dot product be equal to 0? Let us say there are two vectors a and b. When will a dot b equal to 0 if a and b are vectors? That happens only when theta, the angle between them, is 90 degrees. Why? A dot b can be written as a into b into cos theta. This is equal to 0. You know a is a vector, b is a vector. When can a into b into cos theta be 0? When cos theta is equal to 0. And when will be cos theta equal to 0? When theta is equal to 90 degree. This is what you have to understand from this. So w dot xa minus xb equal to 0 means the angle between the vectors xa minus xb and w is 0. What is xa minus xb? It is a vector which is lying on the decision surface. That is this red line. This red vector is xa minus xb, which means your w has to be perpendicular to your decision surface. That is, your w can be a vector like this. This can be w, which is perpendicular to decision surface. So this means w will decide the orientation of your decision surface. So if you find out w, what you can say is, if this is your graph, this is your w, that means your decision surface has to be perpendicular to this vector. That is, it can be This can be your decision surface. This can be your this can be your decision surface. This can be, but it cannot take any other orientation. It can be at any point in the graph, but it has to be in the same orientation because it should make 90 degrees with this vector W. See, all these are making 90 degrees with the vector W. So once you finalize W, you know the exact orientation of your decision surface. So what is the significance of W here? W decides the orientation of your decision surface. So once you get the orientation, what is the next step? That we'll find from W0. Let us see what is the significance of W0. If you want to find the normal distance to a line from any point, let us say I have a random line ax plus by plus c is equal to 0. This is my line, some random line. And let us say I have a point. This point is x1, y1. Okay, x1, y1. This is my point. I want to find the normal distance from this point x1, y1 towards the line ax plus by plus c equal to 0. How do I find the distance? This is the formula. That is, the distance will be equal to mod of ax1 plus by1 plus c whole divided by root of a square plus b square. This is the formula that is used in order to find the distance, normal distance from the point x1, y1 to the line ax plus by plus c equal to 0. So the same equation, if you consider that instead of a random point x1, y1, if it is the origin, that is 0, 0, then the normal distance will become, this ax1 will be 0 because x1 is 0, by1 will also be 0 because y1 is 0. So this boils down to c divided by root of a square plus b square. If you apply the same logic into this equation, here the coefficient is w transpose and w0. If you apply the same logic, you will get d is equal to w0 divided by root of, divided by norm w. This is what you will get. Because instead of root a square plus b square, the corresponding term will be norm w here. And here, ideally, you should have a minus sign in case of this decision boundary. The reason is that if you're having a decision boundary like this, if you're having origin here, this origin will correspond to a point for which the value of y of x is less than 0. So in order to show that sign distance, you generally put a negative sign here. Similarly, if the point is somewhere here, let us say here, this will denote to a point for which y of x is greater than 0. Y of x is greater than 0. In that case, it will be positive. So then you will put a positive sign. Okay. So here, because I'm considering origin to be on the lesser side, I'll put negative sign. So irrespective of the sign, here what you have to understand is that W0 is the key factor in determining the distance of the decision surface from the origin. Okay. Previously, we had seen that W is the key factor. Let me erase this off. We had seen that W is the key factor that decided the orientation of the decision surface. And now we see that W0 is the key factor which decided the distance of the decision surface from the origin. So if you want to plot the decision surface, these are the only two things you want to know. The first thing is, if this is the graph, what you want to know first, you want to know the orientation. So already you know this is your vector W, which means your decision surface can be this, 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 or anything which is perpendicular to this vector W. Okay. The next thing you want to understand is which among these lines to choose. So how do you choose that? You see the distance of the line from the origin. So from the origin, let us say the distance of the line is this much. Okay. In that case, this particular line will be selected and all other lines are discarded. So this is how you find out the decision surface. Your W will tell you the orientation and W0 will tell you how much distant from the origin is the decision surface present. So with these two informations, you will be able to plot the exact decision surface. So before we conclude this lecture, I'll draw neatly in a graph and give a clear picture to you, and then we'll conclude this lecture. So this is how it would look like. Let us say this is your decision surface. So W will be the vector which will decide the orientation. Then let me just extend this parallel line here. So if this distance, this will be denoted by minus of W0 divided by norm W. So these two factors will provide you clear idea of the decision surface. So this decision surface is y of x equal to 0. So any point above this decision surface will have y of x greater than 0, and any point below this decision surface will have y of x less than 0. If any of the points are here which are having a value y of x greater than 0, you will classify them as class C1, and any point below this which is having y of x less than 0, you will classify as class C2. This is how you do two class classification using linear model, linear classification.